Probably is some yeah. So,
Yeah. Um, uh, People always ask me about the best undergrad astronomy program in the state, thinking I'm going to talk about Chapel Hill. And I always say, actually, App State. And in terms of undergrad, grad astronomy, I'd argue that we're perhaps the best. But undergrad astronomy, the program you have there is just amazing. The resources you have for undergrad students, amazing. And you have Elise there now, and
mhm.
Elise worked with me when she was an undergrad way back when, and she just went to my uh, well, as an undergrad, she went to my summer program at Green Bank, and she just went back this year as an educator. So yeah, in fact, I just emailed Dan Caton just 5 minutes ago,
Oh,
saying,
really? Okay.
"Yeah, your DSO 17 telescope has lots of streaks in it, has for months, and so uh, I'm trying to get that sorted out with him because we're short on telescopes right now. It's something we discussed in previous meetings, and it's still the same problem that Tololo, where we have most of the prompt telescopes, we have prompt telescopes all over the place.
Mhm.
In Australia, Canada, we're moving one to Arizona in the next year, but our most of our prompt telescopes and our best prompt telescopes are at Cerro Tololo Inter-American Observatory in Chile. And the lab curriculum depends on these telescopes pretty heavily. And it's been down for 20 some days. The internet, they shut off the internet for 20 some days because there was a hacking attack on, I guess, Gemini North, but they shut down all of Tololo where Gemini South is located precautionarily. And we still don't have access, and labs are beginning. I've opened up, all these telescopes have time sharing agreements, and I've opened up our fraction on prompt meckering, um, and uh, and we're doing some other mitigating measures. We're getting our campus Moorhead telescope up and running. I'm emailing Dan Caton. We're sending a new weather station to Australia to open up some of our Sighting Spring telescopes, even though they're not exactly ready for prime time. But we will try to get through mostly on the back of the Meckering telescope. I hear there we've been talking with the director down there, and they are opening outgoing holes in their firewall. And fortunately, we rebuilt the system a number of years ago that all the communication is directed from the observatory back to Skynet. Skynet never sends, never queries, um, or pushes commands to the telescopes. The telescopes request command, what they should be doing. So if they open a one-way firewall, we should be okay. We just need to make sure that whatever terrible is going on down there that they won't tell us anything about doesn't leak through this opening in the firewall back to UNC. So that's the state of it there. Anyway, um, okay. Well, since you're new, Joseph, everyone else got to give little introductions. Would you like to give a introduction to the group?
Um, okay, so my name is Joseph Holmes, and I'm an adjunct faculty member at Appalachian State University. Some of you came in after we were just talking about this. Um, I got my undergrad at Guilford College, same as actually Elise, Bachelor of Science. And then I went on to get my Master of Science at Appalachian, and then threw a Hail Mary and was like, I need a job. And so they hired me. And so I'm teaching a bunch of sections of both physics and astronomy. And we're slam full on students, and anything I can do to help them out. I've worked at places like Klein Observatory. Actually, I still technically work there, but as a volunteer at the community college there, right? Yeah, and that's where I first saw met you, Dan, when Prompt came online. I believe you gave a talk at TriStar, and yeah, and or not Prompt, but Skynet, and yeah. So I have my hands in a little bit of everything. I still have a key to the Klein Observatory at Guilford College as well. So I'm happy to be here. My research has been mostly I did a lot of exoplanet, like transient type stuff. I like that. I was looking for like TTVs and things on planets that really or stars that had not been really observed too much, as well as heliophysics. I like that. And of course, here at Appalachian, the graduate program is really centered on a lot of engineering and hardware interfacing. So the beauty about like Skynet and like all everything is where the hardware meets the science, and I like that. And then how we can introduce that into the classroom. My mom was a teacher. I love teaching, so let's keep it up. But yeah, I
That's
know we
great.
got.
Yeah, that's great. So yeah, thanks. And it's good to reconnect with you in
Yeah,
person, Zoom. All right, so we're about a week behind. We spent a whole week doing introductions, and we got through kind of most of the orientation materials last time and started in with Lab 1, Week 1. My goal today is to finish Lab 1, Week 1. Maybe we can all put the observations in, and we'll do Lab 1, Week 2 next time. And we'll have a little bit of time at the end, and I'll show you the remaining orientation materials. All right, so let me share my screen. Does anyone else have anything to share or comment on before we
Dan,
dive in? Yeah, go ahead.
hi. Is it okay? I've wondered about this. Is it okay to give the pre-surveys in class?
Yes. Yeah, so pre-surveys, that's the first thing on my list I wanted to talk about. Yeah, there are two pre-surveys, an attitudes pre-survey and a content knowledge pre-survey. And actually, I'm going to put the links in the chat, even though those of you who are teaching OPIS this semester, I've already sent you the links. Oh, where's my Zoom control? Why is this so hard? There it is. Move that up there. Chat. Okay. They're the two links. I'm pretty sure that's this semester's link. In the past, I've sent the wrong ones. There's a different link for the pre and the post every semester. I think those are the right ones. So first, for those who are teaching OPIS this semester, what I often do is the attitudes one. I do that out of class. I'm always very protective of my class time. I hate doing mandatory surveys, and here I'm asking you to do two big mandatory surveys, eating up your class time. So the attitudes one can definitely be done outside of class, just as long as you really push it, really encourage a high response rate. It only counts if we get both pre and post from the student. So the student puts in a number. We tell them to use their student number, something they can remember. But really, any matching number works. But it has to be the same between the pre and the post, and it only really counts for the education researchers if we get both. So high throughputs on each is kind of critical, and you can offer extra credit and all that stuff. The content knowledge, you can do it out of class, though if possible, I encourage you to do that one in class, simply because students have a strong desire to get the right answers, to the point that they will look these things up on the internet, and which totally messes up, we're trying to measure how much they've learned from the pre to the post, how different things can boost this. If we do this or if we do that, can we boost the pre to post change? And if they're looking up one or the other on the internet just because they want to get the right answers, even though you tell them, you don't need to get the right answers here, just an inventory of your knowledge. So anyway, if you're going to do one in class, I do that one in class because they're then not going to look it up online. To give a very long answer to your short question. Also, there's the encouragement video. Let me put that in the chat. And this one was really written for, or videoed for sections that are doing OPIS this semester. Now, the reason I wanted to bring this up today wasn't that stuff, because I've mentioned it, most of that before, but if you're not doing OPIS yet, if you're here learning the curriculum ahead of schedule, which is really the smartest and safest way to go, I'd still love for you to give the pre and post surveys so we can collect baseline data. Most institutions that we deal with, they're offering OPIS, so we can't get baseline data. We get OPIS specific data. But as people are onboarding, if there's the opportunity where they're learning ahead of time, they're teaching it the regular way, to go ahead and give these surveys anyway to establish what the usual gain is. And then when you switch to OPIS, we'll see if there's an improvement. And particularly after one or two, what we've seen is, by the second or third implementation, these scores keep going up before they level off as you become more masterful at it. Okay, so that's that. Any other questions, comments? Okay.
I have kind of a follow-up self-interested one.
Please.
I apologize, but
No,
so
no.
the little cash prize for giving the surveys, how does
Yes.
one organize that?
Yep. So the way it works, I'm going through this now for the past year. So at the end of the year, and for OPIS, it's fall, spring, summer. Is it summer? No, it's fall, spring, summer. Yeah. I have to check on that. I think it may actually be summer, fall, spring. Anyway, we go through 3 semesters, and we collect all the data. We write down how many students did each lab, how many pre-surveys you got of each instrument, how many post-surveys. And once we have all that information, and plus the list of who did the training, we write out the cash amounts. It's $500 for doing the pre and the posts, but you actually have to not fail. Some people will do the pre's and they forget the posts, and we have no matches, so that doesn't count. You got to match them and have matching results for a good fraction of your students. And then we send the information to AUI. They're a partner in the NSF grant, and they will contact you and add you as you do some paperwork with them, one time only, and then you get paid. So it's $500 if you teach and do the surveys, $500 for the training, and $500 for a feedback session at some point during the grant. Like we'll take a semester when there's probably a spring semester and do feedback. Though I haven't worked through all the feedback I got on the last feedback session, so it'll probably be closer to the end of the grant. And it's $500 for the surveys each and every semester until the grant runs out. And we're in year 4. We're going to extend to year 6, so there are 3 years left of that. Other questions? Questions are good. As I said before, I hate just giving a monologue, but discussion's good. Okay, so everyone here has their information on this page, I believe. If you don't, go ahead and add it. I'll put this in the chat as well. And just so I have a list that I make sure I reach out to the right people and don't have to spam the master list. Okay, what's next on my list here? Oh, new instructors. I think this came up last time. I forgot who asked, but if new instructors who aren't attached to a section, excuse me. So if you're teaching OPIS this semester, I've created a section, and we've gone through the process of making sure you have a WebAssign instructor account, and I've attached you to it. But if you're working in advance and you're not teaching OPIS this semester, I did not create a section for you. So just send me an email with your WebAssign username, and I will get you attached to one of my sections so you can see the labs that we'll be continue to look at today in their native environment. There are also PDFs of the labs, but they're really kind of atrocious. The web page does not convert well to a PDF. The labs are meant to be interactive online. So just let me know and I'll attach you to one of mine. I'll set it up so you can't change my students' grades or something. And then you'll be good to go there. I think that's all that I had in announcements, other than, here's the recording from last week. I sent out each week I'll send out an email saying the recording is ready. And so they're starting to accumulate. And again, today we'll finish lab 1, week 1, and the remaining orientation stuff. And again, I mentioned this before, if you're already ahead of the schedule, you can always go to the previous year's recordings and get ahead of the trainings that way. Okay. Where we left off, we were on WebAssign, starting to go through lab 1. I'll go to one of my sections and I'll pull, I already have it open. Slide on up here at the top. I was messing with it. Let me close down. There we go. It just reopened on top. So when you first open it, as I pointed out last time, there is at the top a student view. If you want to see it as the students do, you can go here, or you can just grab it from the instructor view. That's what we're doing right now. And the student view looks a little bit better. Now, last time we went through this stuff at the top. This is the instructions area. And it's a little bit different than the rest of the lab in that I have the freedom to edit this whenever I want. And we talked about the different things. We have the videos, the kind of overview videos, and the different information that students will see here and most likely ignore, but yeah, at least it's there so you can claim they were told. And now let's get down into lab 1, week 1. Most of these labs fit in a single question. Now, of course, there are tons of questions. If I open up any of these sections, you can see there are tons of boxes for them to fill in. And each of those are a question. But it's a terminology thing. In WebAssign, you can have a question made up of lots of questions. And so this whole thing here is a question. This whole thing here is a question. In most labs, it's a single unit, a single question with lots of sub-questions. But this one was too long. I think lab 8 is also too long, so they break it down into 2 parts. But it worked out just fine because we have a week 1 and a week 2. Week 1, they're learning background information about how Skynet works, and they're putting in their Skynet observations, most of which will be ready for week 2. That's the idea. There's actually no questions for them to answer in week 1. But there are lots of things we'll do in week 2 using our Afterglow software once the images come back. Let's just start working our way through here. So first we have the goals, and this is the goals for both week 1 and week 2. The first one pertains to week 1. They're going to learn how to use Skynet, how to place observations. Oh, question, Britt, go ahead.
Yeah, sorry, I hate to derail you. Just quickly, I noticed that there's homework. There's a section on homework that's meant to be done before the lab. Did you say that already? Sorry. Is that right?
No. What I do is in my sections, I tell the students they're responsible for reading through or at least skimming carefully the lab ahead of time, watching videos ahead of time so they come in prepared. And we give them like a 5-question quiz. Really simple stuff. Just as long as they at least skim the lab, they'll be fine. But if they didn't look at all, they'll lose points. But I don't give them any homework ahead of time other than that.
Okay. But the section that says Introduction to Skynet homework, is that?
Homework. Where's it?
That's what I see when I log into this page, the very top of the page. There. Right? This, yeah. Sorry, I'm looking at the student view. And when I see this, it says homework at the top where it says Lab 1 Introduction to Skynet. So that's like a pre-lab activity.
No, so I think that's a
Okay.
terminology thing. I think WebAssign calls these things homeworks, even if they're labs.
Ah, okay. Thank
I think
you.
that's it. That's probably it.
Okay, thanks.
Okay. So the goals. In week one, they're just going to learn what Skynet is, what prompt is, where the prompt telescopes are. Those are the good telescopes in the system. There are also some good ones that are not prompt telescopes, but these are uniformly good. These are the ones that my group maintains, and it's the largest in number. And they're just going to learn how to put their observations into the system, and they're going to put the observations in. Then in week two, when most of their images come back, they're going to start to learn our Afterglow software. This is our web-based image processing, image analysis software. It's meant to essentially become a replacement for Astro Image J, which is really medical imaging software that's been perverted to serve astronomy. About $1 million has gone into the development of Afterglow, and it continues to get better all the time between NSF and DoD funding. Anyway, in week two, they're going to start picking up developing a toolkit. The skills they're going to learn is they're going to learn how to adjust the brightness and contrast levels in their, we're starting simple. Adjust the brightness and contrast in their astronomical images. Astronomical images tend to be 16-bit depth. It's more information than the human eye can see. So you have to decide whether to focus on the bright stuff or the faint stuff and how to adjust the brightness and contrast. So you're looking at the details of Jupiter, or maybe you're washing out Jupiter, but now you can see Jupiter's moons, that kind of thing. They're going to learn how to measure angles in their image, the sizes of objects or the distances between objects. That's an important skill. And also how to identify objects in their images that are moving, such as moons going around a planet. They'll learn how to call it up in stellarium and compare and contrast and identify their moons. And also dwarf planets. They image some dwarf planets, which just look like a star. They're so far away that it's just a point of flight. But how do they know which point of flight is the dwarf planet? They compare it to archival digitized sky survey DSS images, and we show them how to do that as well. So the science objectives of this particular lab are not that deep. It's more about getting them excited. They're going to shoot all sorts of targets, mostly solar system targets, because they're short exposure time. It doesn't break the credit bank. They also get to image a few deep sky objects and to learn some basic skills as they're having fun. I often like to start with MWU, the follow-up lab sequence. We start the same way. It's not scientifically deep, but it's they do a color mosaic of the moon in the next course to start out, just because the results are fantastic and it generates excitement, and they learn some skills that will scaffold as they go. Okay, so those are the goals. But for week one, it's primarily this first goal. Equipment, as you can see here, it's an accordion type setup. Equipment is real simple for this lab. They just need a computer with an internet connection. Doesn't even have to be a good computer. It has to have a browser that's fairly modern, but Skynet works on pretty much any browser platform. If they're running too old of a version, they may have to update, but that's never really seems to be a problem. In terms of computation, most of the heavy computation, we've designed it to be server side on Skynet, but especially Afterglow. Like if you want to batch photometer 1,000 stars in 100 images, we're not going to make their computer do that. We'll do that on our servers and pass the results over. Okay, and then the background sections. These are, of course, the sections students never read, which is why we have videos summarizing the background sections up here. But let's go through these quickly. First, we just introduce them to the prompt sites. Again, Skynet's the larger thing. Prompt is the UNC subset that we take care of. And as I already said, our primary site is Cerro Tololo Inter-American Observatory in the Chilean Andes. And I often tell the students it's the third best place on Earth to observe, where the best place is the South Pole, but very expensive, hard to operate there. Next best place is probably Mauna Kea in Hawaii. And after that, you have the Chilean Andes. And we built there because UNC already had its 4-meter SOAR telescope being built there. And so we got an in back when there was still space on the mountain. Now it's very hard to get on this mountain. So we have 8 telescopes there, which is pretty fantastic. There's some fun videos in here as well. This is how to build 6 telescopes in 60 seconds. This is when we first built the telescopes in 04 and 05. We took a picture from a webcam every 10 seconds and pieced it together into a movie, initially 45 minutes long, but then we cut out nights and in bad weather and got it down to a minute. And they can watch them being built. There's also a 30-second version, though we were advised not to link to that because with the motion of the sun and the speed of it, it could actually trigger epilepsy, epileptic seizures, possibly. So we went with the slower one here. But anyway, that's kind of fun. And this is actually what it looks like when you're there. Often photographs you can go deeper, but to the human eye, you look up and that's what you see. This is Venus, and these are prompt telescopes. As I said, we also have sites in Australia, 3 sites, though currently only 1 is connected. 2 are connected. 2 scopes are connected, 1 prompt and 1 non-prompt. But there will eventually be 5 prompt telescopes in Australia, and some of them will pop online probably in the next week. And we have 2 more in Canada, the second still being set up, and it will eventually be moved to Mount Lemmon in Arizona. So there'll be a prompt Arizona site pretty soon. Here's a picture of our sighting spring. This is the site in Australia, this National Observatory in Australia. And one of these scopes we've moved over to Perth on the other side of the continent to give us some more weather reliability. Here's another little fun video you can show them. This is back with the original 6. We've since built 2 more telescopes, larger telescopes. This is what happens every night when the sun gets 1 degree below the horizon. The domes open automatically. The telescopes slew into position to take calibration observations. About a third of the observations we take are not astronomical observations, but biases, darks, and flats. And we don't actually spend any time teaching them about biases, darks, and flats in this course. Skynet creates masters and reduces the data for them automatically as long as the masters are available. Again, we're trying to get them straight to the science. And finally, there's a link here to live webcams in Chile, but the link is broken. And I sent some improvements to WebAssign. They forgot to update to the new link. But even so, with the new link, since the internet's down, it doesn't go anywhere. But I have a few screen captures here of what it looks like and will look like. It takes you over to a place on Skynet. This is from last year's training. And this is the webcams on the top of the mountain looking down at all the small telescopes. There are large telescopes on the mountain, but they're behind you in this picture. And you can see there the prompt 6, and there are 2 more, the prompt 6, and then 2 more here and here. They're also part of prompt. And these are Las Cumbres telescopes that have been added more recently. And you can also, from where this link normally goes, you can navigate and see internal webcams of the telescopes as well. And these are live views. And so if one happens to move, you can catch it. Though, of course, most of the motion occurs at night when it's dark. But if the moon's up, you can still see what's going on. So that's fun. So just some introductory stuff there. This section is telling a little bit about why we built the telescopes. Initially built them to chase gamma ray bursts. And back when that was a very hot field, now it's not as exciting in my mind. I've moved on from it. But back then, the reason I got into this is in 2000, when I was a grad student, my advisor and I wrote a paper saying you could find gamma ray bursts farther out than anything that's ever been discovered, and then use them as probes of the early universe, which motivated me to change to instrumentation, even though I'm terrible at it. but fortunately we had some success and I could raise money and hire people who are good at it to build kind of a photo Z finder. The reason we have a bunch of small telescopes is they can all salute quickly, and initially they were all optimized for different wavelengths. And these gamma ray bursts, they emit across the spectrum, but the ultraviolet's gobbled up by hydrogen in the host galaxy, and that gets redshifted into the optical band. And so how far it goes gives us the distance. That was the original plan. And we started building these in 04, and by 05, we discovered the most distant explosion in the universe out at redshift 6.3, which is 12.9 billion light years back in time. The universe is only 13.8, so we broke into the first billion years within the first 9 months of operation. We're just dumb luck. It took years before anyone beat the record. And I don't have this here to show off. The reason it's here is it's important for the students to know that these telescopes are being used by professional scientists to do science and cutting edge science. That makes it so much more exciting for them. We're using the same interface that they're using. The Skynet's Q scheduler says, okay, we're doing a professional observation. Okay, that's done. Let's grab a student observation, another student observation. Okay, over the pros, back to students. They're using the exact same system as the pros. And that's really, the education research results are showing that's important that they understand that. I should say that, nowadays, Skynet data is published in peer-reviewed journals every 20 days on average. And 4 or 5 times we've hit Nature or Science. We were the first to discover rings around something other than the gas giants in the solar system. Centaur, which is a large object between Saturn and Uranus called Chiricolo, and they've now discovered rings around some other minor bodies in the solar system. We've detected colliding planets, making giant dust clouds that would obscure their star, and many other things that have made it to that kind of upper echelon. So it's good for the students to know that they're privileged to use the exact same system. Okay, then a unit on how a telescope works. And we talked about the philosophy of this a little bit last time. It's not the main point here. The old labs that we would all do, and still do to some degree, taking the students out at night to play with / fight with small telescopes to observe things that don't really connect with what you're teaching in lecture. That's what the labs were. And so the whole point of this is now these are professional scopes, and the system is good enough that they don't have to do that fighting aspect, and they can get straight to quality data that does connect with the greatest hits of the past 400 years, the content of introductory astronomy lectures. That said, they should know a little bit about how telescopes work. But again, the philosophy is astro majors really need to learn how telescopes work. Here, what I would recommend is bringing in a small telescope. Now, here's a picture of me next to one. The joke is to make it look cool, but yeah, it's really, for scale. So they have an idea of how, this is the smaller ones. This is a 16-inch telescope. They go up to 32-inch. And we've replaced the mounts with better plane wave mounts. Anyway, this gives a sense of scale. And here's a diagram, but if you have a little telescope, bring it into class and you can point out the same things, and it becomes more meaningful, I think. But in short, I know all the stuff I'm about to tell you, I know but as you might present it to a student, light comes in, bounces off the primary, bounces off the secondary, goes through a light baffle, which is a tube blocking like straight lunar light as much as possible, through a hole in the primary that makes it a Cassegrain telescope, and then through a filter wheel and a camera. Rides on a mount, and we mentioned somewhere in here, the most important part of the telescope is the mount. If you can't point accurately, track perfectly, right? The telescope's sitting on a rotating planet. So these telescopes have to rotate in the exact way in the opposite direction. If they don't do that well, you get blurry images. The mount is critical. We've upgraded all the mounts. The least important part of the telescope is the telescope, actually. The camera is much more important. But I like to focus on the camera with the students. This camera right here $15,000. And the bigger ones we have now are close to $60,000. This one is 1 megapixel black and white. And compared, they have many megapixels on their phone in color. And so this, why are we using such terrible cameras, and why is it so expensive? And there are a couple reasons. One reason is these can see in the dark, and their cameras can't. And if they don't believe me, I give them the homework of locking themselves in a dark closet and taking a selfie, and just jokingly. And they won't see anything, but ours can see in the dark. Also, black and white. They're black and white because on their color cameras, each pixel is divided into red, green, blue. And stars only occupy a few pixels, so astronomers would then want to know how much red light is under the green part of the detector, how much blue light's under the red part. You can't do it. So we have monochromatic black and white cameras, and we use a filter wheel. And the way it works is you take a black and white picture of red light, black and white picture of green light, black and white picture of blue light, and you put them together into a colored picture. Now, as I mentioned before, OPIS is primarily black and white single shot science. So single exposure, stuff that you could do on a single exposure. We're not trying to make color pictures. We're not trying to make pretty pictures. That's the point of the follow-up curriculum. That said, there's such demand for this. I've added a little bit where if they want, they can spend some of their 30-minute allotment doing this for fun. There's a video, I'll point it out in a few subsections. Maybe you do it early on, maybe you save it for the end as a treat. Maybe some students are going to dive in and do it anyway. And some students will burn through their credits. They figure out how to make the color pictures and they go nuts, and then they find themselves with no credits to complete the rest of the labs. And that's okay, because that is your future astronomer. And so you don't punish them. When I set up your sections, I give you some extra credits anyway. Just replenish their account. And if you run out, let me know and I'll give you more. And almost done with background. There's a little bit here on maintenance. These are real world systems and real world conditions. They do break. That's why we encourage students, when they put their observations in, to put them on as many telescopes as possible. So if 1 or 2 go down, there's still others that can complete the observation, or if some are weathered out, there's still others that can complete the observation. First available will carry it out. Most failure modes can be corrected by Skynet, even without alerting us. Some things it can't fix, and it lets us know, and we log on, we can fix remotely. Other things we have to call up the site. And some things, like a broken camera, we could be down for months, though we do try to maintain some spares. So there's a range of different failure modes, and they just need to be prepared. Like right now, the internet's down to Sertololo, has been for a month. So there are things that can go wrong. And lastly, there's a section here on the broader Skynet network. They can click here to see what telescopes are available here, and see telescope details and what ones are currently connected. I'll show you that in just a second. But now let's get to placing the observations. That's kind of the background. So now we're getting into the procedure. Any questions on background stuff?
I have a question about, do you use exclusively CCD cameras? And is there any reason not to use CMOS cameras?
We are moving towards CMOS. They've been tricky to use in the past. They're getting better. One of the issues is they're shutterless. And so if you want to, get biases, you need to put a blank in your filter wheel. And so we're working on that. There are a couple CMOSs on the system, and eventually it'll all be CMOSs because people aren't making CCDs anymore. Or it's becoming more difficult and you have to pay more. So we will be switching over to CMOSs and are in the process of doing so. But the prompt telescopes currently are all CCD based, except maybe one of them, I think. Okay. All the equipment gets updated in time as necessary and usually not before necessary. So procedure, observing with Skynet. So we tell them to go to the Skynet site. There's a link here and there's a video tutorial on how to do it. And then we hit the highlights of the video here. So it's not a complete set of written instructions. the complete set of instructions in the video. And the reason for this is the website's always changing. And as I mentioned, hopefully by May, we'll be scrapping the entire current Skynet site and replacing it with Skynet 2, which has been in dev for a couple years now and will be quite spectacular. But let's just go over to Skynet and I'll show you how this works. Here's Skynet. Go back to the home page for a second. So it'll look like this when you come here. When you go to My Observatory, you'll see optical observing, radio observing, my account for changing passwords. And once you have students of your own, you'll have group management. This other stuff's above your pay grade. It's managing multiple owners of telescopes, site administration, stuff like that. If you have a telescope on Skynet, you'll have access to some of those. I'll come back here in a second. Here's Skynet Live, and you can see the current sad state of our system, but it's not that bad. Here's our radio telescope. Most are in our hemisphere, so the sun is up, but the sun is down here. This is one of the Australian telescopes. And here's the other. This one's in Perth nearby. Meckering's about 100 kilometers east of Perth. So we got two Australian scopes here right now, and so they're both being used. And this one's in Poland, and it's doing its post observing darks. It's doing darks in advance of sunset here. So it's starting to ramp itself up. These two are in action. And we can see the names here if you have administrative privileges. Otherwise, the names are hidden for privacy reasons. Okay. And bad weather in some sites, and some are locked. If the weather's bad, sometimes they lock them in a precautionary way. And then over here, we have info on each site. If I go to Tololo, you can see recent images, nothing for the past 26 days because of the internet blackout. And normally this is where this picture appears. Not picture, live stream of the site. But of course, without the internet, it's blank right now. And you can go and look at any particular telescopes page. These are the last ones taken by the Prompt 6 telescope. And there you see the internal view as well. Okay. So how to put an observation in? Let's go to optical observing. Waiting for Skynet. There we go. Okay, it first takes you, when you go to optical observing, a list of all your observations. If you've never used Skynet, I just took this one an hour ago. So I was just testing a few things out, and this came through from Meckering. Anyway, it shows you your recent observations that you took and all your ongoing observations. If you haven't done anything yet, it's blank, but soon you'll fill this up, and I probably have hundreds of pages here. To add there's search features as well for finding stuff, both your observations, your groups, or your consortiums, your collaboration. Let's go to add a new observation. And this is all in the videos. So if I go a little quick, don't worry, you can watch the videos. And there are many different ways to pick a target. Here, this right here is something called Sky Viewer. Now in Skynet 2, we've rebuilt this tremendously. We've essentially rebuilt half a stellarium in the browser. It's really exciting. All sorts of things you can do. This is a very simplified version. I should say there's a tabular version for those with blind, visually impaired, with impairments, because they're using screen readers, and all of our interfaces we try to make compatible with screen readers. Anyway, most people here, I'll just select now. Oh, it's set to Meckering right now. So, I can zoom in to any particular region of interest. Maybe I'll select M2 there, brings up a DSS preview. And observation name, you can edit it. M2 is awesome. No, it's a glob. Globs aren't awesome. Globs are okay. M2 is okay to observe. Anyway, you can call it whatever you want. It puts in the coordinates here. If it's a moving object, don't worry, we'll update the coordinates before dispatching. For these students, this is how we set the observations. For max sun angle, we recommend -12. Pros don't start looking till the sun's 18 degrees down. So we tell the students -12 because they're looking at big, bright stuff. That should be good enough, and it gives them a chance to crank stuff out before the pros start dominating the time. The target needs to be a certain number of degrees above the horizon. We tell the pros use 30. We tell the students to use 20. They can have slightly, no, the atmosphere is not bad down there either. If you go too low, the atmospheric blurring becomes a problem. And it needs to be up for a certain amount of time. We tell the students to use half an hour. If it's not up for even half an hour, odds are they're not going to get it. These are new max moon phase and moon separation. The default, and I need to add this to the instructions. For OPIS, the default should be 130. We're willing to look even under full moon conditions as long as the moon's 30 degrees away. For more serious stuff, we dial that stuff back, like in the MWU course. The only difference is if they're looking at the moon itself, they need to change that to 0. And these are instructions that I need to add to Lab 1, and I'll send that stuff to WebAssign probably in a day or two. We have advanced settings for dithering and offsets. They don't need to worry about that. And then we have an air mass chart here. Let me put in a good demo one is the Tarantula Nebula. Because it's a good southern hemisphere target. It's circumpolar, so it's always up. And you can see here, it's currently observable from Australia. And then in a certain number of hours, it would be observable from Chile. If I pick a more northern hemisphere object, there's M2 again. We have lots and lots of curves because we have lots and lots of sites. The next thing they do is actually let's do a planet. Let's do Jupiter. Jupiter's just coming up. Let's do Saturn. Maybe we can actually get a real-time response from an Australian telescope. There it is. Saturn's right here, very close to the full moon. I don't know if that's going to be the best choice, but let's see what happens. -12, 20.5, 100. Oh, I better lower this. If I want Saturn right now, that close to the moon, I'll tweak it. But normally the students would have 30, and it would just wait a couple days until you get some separation. Then it would carry out the observation. But I'm going to see if I can get one back of Saturn right now. Choose filter. The filters they should use and the exposure times are written in the lab. You may want to, let me check the lab real quick and see what it recommends. For Saturn, if I want to observe the planet Saturn, it tells me to use B band 0.3 seconds. Okay, so B band, and you see when I selected that, I lost a few telescopes. A few telescopes don't have a B filter, but most of them do. So that's pretty good. For really bright stuff, we'll use U band. Like Jupiter, we tend to use U band because it blocks a lot of the light. Save and continue. Now we select, I should go back just a second here under filters. You can select multiple. Like if I select U and B and maybe some obscure filter like S2, you see I'm just losing telescopes left and right. It's an and. If you want, or we have generic filters. Like I can select low through and it will, any filter that cuts out most of the light, like narrow band filters, U band filters, and here I'm saying I'll take any of those. But let's go back to B because that's what was recommended for Saturn. Save and continue. Then you pick your telescopes. And normally, you know, if there's plenty of time, I say go looking for the prompt telescopes. Of course, all of Tololo's down right now, so I'll just skip that. Well, I mean, I can select them in case Kalila magically comes back up tonight or something. Here's one in Australia. Here's one in Canada. You can select other ones if you want, but these are the guaranteed likely good ones. And I don't think I have prompt 3 in the same time account. Here, I'll just make it simple. Prompt 2, prompt 5, prompt 6. Yeah, that first one has been taken offline. So that one should take. Yeah, that took. But I'm going to go back. Instead of just selecting prompt telescopes, I should use the breadcrumbs to go back. You can also select all telescopes by clicking on the orange dot, all telescopes in your time account. And I'll do that. It'll pick up some non-prompt telescopes. This is if you're more desperate. You're running out of time. I'll just do that right now. So I have lots here to show you. And then it takes us to our exposure page. Now, we are a heterogeneous system. Each telescope is different throughputs, different efficiencies. So the way the OPIS labs mostly are built is you select the generic system. You're going to design it for a generic telescope, a 16-inch telescope at Tololo. And what I say was 0.3 second exposure. And then you can slide over each one, and it tells you the max permitted. When looking at this target, being a bright target, it permits a certain maximum. And for most of these, I am under the max. Also, if you're looking like a faint thing and you have like 100-second exposure, I skipped a step here. What it's doing, you see the numbers change from scope to scope. That 100-second on the generic scope corresponds to 123 seconds prompt MO. It's scaling the exposure because it knows the measuring telescope is not as good as the generic telescope. So it's giving you a slightly longer exposure time to compensate. If I have a better scope here, it'll be a shorter exposure time. Basically, it will adjust the exposure time so you get the same signal to noise as in your design telescope. So you design for a single system and it will adjust the exposure times to give you the same depth. And the Skynet system is constantly checking. It takes all the observations that come in, calculates limiting magnitudes, and figures out how good one telescope is with respect to the other. Different amounts of time, but same amount of credits. A big telescope, you'll spend more credits per second. A small telescope, you'll spend fewer credits per second because you'll need more seconds to have the same signal to noise. Did that make sense? I don't feel like I explained it very well, but the credits give you signal to noise. And so you design it for a single system and it will automatically adjust for all the different characteristics of the other telescopes. And normally if something is, if the adjusted time is too long, and these are all too long because it knows I'm looking at a bright source. It's giving me the maximum there. These will turn pink. I don't know why they're not turning pink. I emailed my programmers this morning, but you'll know that if you put in an exposure time that rules out certain telescopes, they go pink. And as long as you have some left, you're good. I'm going to go back to the 1.3 second exposure. Advanced options down here we don't need to worry about. Save and continue. Takes me to a checkout screen. I'm submitting it. It's being entered into the database. And now it's here and it's active. Once it's completed, let's say here's a Saturn that I took last week from Meckering. And so there it is. And they're often shocked by how tiny it is. But using the Afterglow software, we'll be able to zoom in, adjust brightness and contrast, and get a lot out of that. Now, if we go back to the lab, again, I've gone too slow, but we can speed through a lot of it now. That's how you put an observation on the system, how to check it. Things they should look for when checking. About 20% of their observations will be ruined, and they need to resubmit them. So they need to submit early and check often. They can't submit and just assume everything will be okay, and the night before the lab is due, open things up and realize they had a problem. Things that can go wrong, it could be cloudy. We do have cloud sensors, but they check one part of the sky, not necessarily the part of the sky where the telescope's pointed. If you're clouded out, you end up seeing the response pattern of your CCD. In blue filters, you can actually see the scraping when they manufactured the CCD. This is a red filter, and you also see dust on the camera lens, out of focus dust. Here's partial cloudiness, so you get a mix of those dust donuts and your target. Here's windy night. Here the mount's pointing model is off. I should point out with Jupiter, Saturn, and Venus, Skynet will purposefully offset it about halfway up or halfway down the chip, just to keep it off the center. Bright things will burn a residual image into the chip for about 20 minutes. And so we try to keep bright things off the center to not disturb the professionals who put their stuff at the center. Here's if the tracking stopped working. The stars are just streaming through, out of focus. This is a common one. The shutter, it's the part that moves the most, so it's the part that breaks the most. If you have a sticky shutter, it doesn't close completely. As the CCD is reading out, you get these lines. Or here you can see the iris shutter stuck in position. Here the moon is too close, or someone left the light on. Satellite, if you have two of these, it's an airplane. You can tell the students, suppose it's a 747, look up the wingspan and measure the angular separation. Assuming there's no projection effect, they can actually calculate the distance to the airplane. Fun little side exercise. And sometimes you literally have a bug in the system. We've seen this 3 times now, a bug sitting on the camera window through the filter wheel. The rest of these are putting in their observations. So for the planets, we recommend filters and exposure times, U for the bright stuff, B for the fainter stuff. Again, we try to set their expectations. They're expecting pictures like the ones that have come back from missions that we sent to the planets. And so you really have to set expectations. I'll tell you more about that in a little bit. The moons, the big and medium moons, again, you target the planet, but we have filters that let through more light and appropriate exposure times. And once you adjust the brightness and contrast, you'll probably saturate out the planet, but allows you to see the moons. Again, here's an example of that offset that Jupiter will get. We put in observations of dwarf planet Ceres, Pluto, Haumea, and Makemake, not Eris. You can do Eris, but it eats up a lot of time. Haumea and Makemake, these are getting pretty long, 160 seconds each. But again, we set their expectations. It's just going to look like a star. And in the analysis, they'll figure out which star it is. It's a Where's Waldo exercise, but it's not as daunting as it seems. They observe deep sky objects. We tell them to pick one from each of these categories. This is their splurge. A nebula, a star cluster, and a galaxy. And I'll be updating these lists with more expansive lists pretty soon. But they love this. They love the freedom of choice. They go in and they'll research all of these, picking the one they want. It's so much better if they have a choice to make instead of saying, you must observe this. If they have a choice to make, they really get into it. And so they put in a high-through observation with a certain duration and get a pretty black and white picture. And lastly, last thing we're going to do today, I may go a minute or two over, is their lunar observation. So let me show you how this works. I'm going to go to optical observing, going to add a new observation, and we're going to look at the moon, which is right next to what I was just observing. Zoom in and take a look at this. And right now we're looking at a full moon, which is pretty boring. Let's pretend, let's go forward a couple days, 4, 5. So let's pretend it's 5 days from now and the students are doing this exercise. So here you can see where the terminator is. I'll stop the clock there. And they have the ability to position this. But the first thing they really need to do is select their telescope. This one, unlike the others, will be designed for a single telescope because each telescope has a different field of view. So just checking my numbers here, minus 12, 20.5, 100. And for this one, since we're looking at the moon, the min-moon separation has to be 0. Get rid of the advanced settings. Choose filters. The lab tells them to use a low-through filter. Save and continue. And they pick a telescope. And shouldn't pick a chilly one right now, but let's pick that one in Australia, prompt Meckering. And then they can go back now that they've selected their telescope. And with all these telescopes, it gives you field of view. If you have a larger field of view available, you might want to use it. And if you have a Ceratololo telescope available, you might want to use it because it'll give you a really crisp image. The best imaging is going to come from Tololo. But I selected a Meckering scope. I've come here. I'm already set to Meckering Observatory with the prompt MO telescope. And so they then position it. And, don't position it here that you won't see anything. You kind of want to get the terminator so you can get those really great craters. But keep in mind, it may be an evening or two before it dispatches, and the terminator moves from right to left. So, you may want to move it a little bit to the left, knowing that the terminator will advance a bit. So maybe I'll pick that one right there. You got to save it again. Can't use the breadcrumbs. You got to save it for it to take. Save. Telescope's already been selected. Save. It didn't get selected. Where is here? Prompt MO. Save. And for this one, I don't think you need the generic. I can't remember. That shouldn't matter much, but we're going to do 0.1 second exposure in the low through filter. Save. Submit. There it is, active. And here's one I put in just a little bit ago to practice. I picked pretty much the same spot, though of course it's a full moon right now, so there's no terminator. And again, they'll learn how to perfect this image in Afterglow in week 2 of the lab. But that's pretty exciting for a student to get something like that back. In fact, this one came back within minutes. I wouldn't be surprised if I go to Skynet Live that once this exposure completes, mine comes up and you can see this stuff happening in real time. Anyway, that is, I think, it for today. Well, except this last bit right here. The last bit of week 1 is beyond the labs. They do want to make a color image. We give them some information on what the filters mean, on being careful setting their exposure time so they don't saturate. And I added a tutorial on how to make a simple red, green, blue image, and then how to make kind of more advanced ones if they want to go there, but combining just a single red, single green, single blue into an image. We do far more complicated things with stacking and luminance filters in the follow-up course, but this is doable for the OPIS students and is a lot of fun. So it's there for those who want to do it. Okay, I've gone 4 minutes over. Thanks for the patience. And again, I have another 10 minutes or so before my TAs come here, so I can stick around and answer questions. I didn't get to showing you the additional orientation resources, but I'll try to squeeze that in next time. All right, if there's nothing else, I'll stop the recording.